Today I would like to present some new results on modeling of the influence of atmospheric gravity wave perturbations on the localization of infrasound field and its sources. At present time, infrasound community has realized that wind velocity and temperature fluctuations caused by atmospheric gravity waves play an important role in infrasound propagation in real atmosphere. This perturbation causes fluctuations in the travel time, amplitude and direction of propagation of infrasound signals. Also, they lead to the error in determining the location and power of various infrasound sources such as explosions, volcanoes, meteoroids, thunderstorms, tornadoes and others. Correctly accounting for the influence of these perturbations on the parameters of infrasound signals is crucial for the solving of the problem of infrasound monitoring of natural and anthropogenic sources. There are different models of atmospheric gravity wave perturbations. Most of them constrained so that the vertical wave number spectra of these perturbations follow the universal power law decay with decreasing vertical scales of the perturbations, and the spectrum takes a -3 slope when the vertical scales decrease in the stratosphere, for example, between 2 kilometers to 100 meters. However, these models do not take into account that horizontal wave number spectrum also takes some universal form with the -3 power law decay in some range of horizontal scales. The existence of such a steep horizontal spectrum was confirmed in the aircraft measurements of the wind velocity and temperature fluctuations in the stably stratified upper atmosphere over Arctic region of Russia and over Greenland. These results of aircraft measurements are presented in the papers shown here. Here are shown the vertical effective sound speed profiles taken from the nonlinear model of formation of gravity wave spectrum. These profiles are taken with horizontal step of 28 kilometers. The main mechanism of formation of the spectrum is the advection of each gravity wave by the wind caused by all the other waves. Here is shown the acoustic field calculated by pseudo-differential parabolic equation method developed by Konstantin Avilov. We can see that there are waveguide channels in some atmospheric layers, for instance between heights of 50 and 80 kilometers. These waveguides have finite horizontal extent, and the intensity within these layers significantly increases, whereas in other layers this intensity is very weak. So this so-called effect of intermittency and localization of the infrasound field intensity is caused by multiple scattering of the infrasound field by gravity wave perturbations. Here are shown the vertical profiles of the intensity of infrasound field at different horizontal distances from the source. We can see the vertical oscillations in the infrasound intensity with periods of 2 km or shorter. When filtering these oscillations with periods less than 5 km, we constructed the vertical wave number spectra of these fluctuations at different distances from the source, and we can see that these spectra take very similar shape and decay with decreasing vertical scale of the fluctuations from 2 km to 100 meter with the power close to -3. So this spectra is very similar to the vertical spectra for the effective sound speed fluctuations in the atmosphere, and this is actually the result of scattering, multiple scattering of infrasound field by these gravity wave perturbations. The scattering of infrasound field by gravity wave perturbations also leads to the additional attenuation of the infrasound field intensity with increasing the distance from the source. Compared to the model atmosphere without perturbations, or compared to the model of the atmosphere with only one vertical profile of gravity wave perturbations. We also studied the effect of a fine-scale layer structure of the atmosphere on infrasound signals from fragmenting meteoroids. This work was done in tight cooperation with Elizabeth Silber. We considered two different models of the atmosphere. One model is with varying effective sound speed fluctuations with horizontal distance from the source. Second model is when gravity wave perturbations are concentrated only within stratospheric layer between 37 and 45 km altitudes. This simplified model was taken to isolate the effect of propagation of the acoustic signals through this layer or reflecting from this layer. The partial reflections from this layer is shown in the calculation of the acoustic field from the source, which is at a height of 35 km above ground. This source is below the stratospheric layer with perturbations. We can see that in this case the ray paths have turning points near ground at ranges more than 100 kilometers. So there is a shadow zone between 100 kilometers and 200 kilometers. However, the partial reflections from the gravity wave perturbations in the stratospheric layer and diffraction effects near caustics formed near the ground results in the penetration of infrasound field into this acoustic shadow zone. As a result, there is there arises a long-lasting tail in time after the main direct arrival of the signal, and this long-lasting tail shown here is obtained due to partial reflection of the signal from the stratospheric layer with perturbations. This tail was found also in the recorded signals shown here, and the correlation analysis of the signals at 3 receivers confirms the existence of this tail, and it maintains its azimuth horizontal phase speed in time, as you can see from the results of correlation analysis. So we found the effects of infrasound intensity, intermittency, and localization in some atmospheric layers. The vertical spectra of the intensity oscillation at different distances from the source take a well-defined shape with a mean slope of -3. Also, we found that there is additional attenuation of infrasound field with increasing distance from a source due to its multiple scattering by gravity wave perturbations. The partial reflections of infrasound signals generated by meteoroids caused by fine-scale layered structure in the stratosphere form multiple arrivals and a long-lasting tail in the observed signals. Thank you for your attention.
Thank you very much, Igor, for this very interesting presentation. Igor, you are online, right?
Right, I am online.
Very good, Igor. We got a question from the audience. I will read it for you.
Okay.
The question is, what is your suggestion on how to use these results when analyzing infrasound data for treaty relevant phenomena?
I think that the results of penetration of infrasound field to the shadow zone, when we can detect the source, this is a very interesting result, which is caused by gravity wave perturbations. I think that this may be the application of the results.
Okay, and Ronan, you had a follow-up question?
Yeah, thank you very much. And I was wondering, do you think that it would be possible to, in a few years, maybe to include this in the calculations that are made? You saw very nice calculation, provided that we have sufficient information about the state of the atmosphere?
Yes, of course, we need the current state of the atmosphere to predict the this distribution of the infrasound field. But I think that even if we don't know exactly the real profile, we know the mean real profile, which is not very much differs from time to time, but the gravity wave perturbations have very high gradients, and they actually scatter the infrasound field much more than those gradients in the real mean profile. That's why we of course need the current state of the atmosphere, but we also need the model that of the gravity wave perturbations which will be superimposed on this mean profile.
Thank you very much.
Igor, one final question from the audience. Is ray theory applicable for low frequency acoustic waves, or do you have a modified model?
Of course, this is applicable for low frequency infrasound waves.
Thank you very much. As you know, we have different types of audience, so we are very thankful to you and to all the authors to consider that we may have questions coming from all different angles. So with this, we would like Igor to thank you very much for having submitted your contribution, for being present during the questions and answer sessions, and we look forward to seeing you live in future science and technology conferences. Thank you very much, Igor.
Thank you to you. Thank you.
Thank you.